Hello, SAS Global Forum. I am Bruce Lund. My topic is weight of evidence, dummy variables, and degrees of freedom. This presentation applies to binary logistic models. It answers the question, how to assign degrees of freedom to weight of evidence predictors when running forward selection to minimize AIC. Here are the goals for the presentation. First of all, let's let D be a discrete predictor, nominal, ordinal, numeric, with only a few levels. Now we will explain the weight of evidence coding for predictor D. Weight of evidence is an alternative to dummy variable coding for D. Then we will explain the degrees of freedom problem for weight of evidence coding and propose a process to adjust the degrees of freedom for a weight of evidence coded predictor. Use the adjusted degrees of freedom in forward selection of predictors, weight of evidence, and other predictors to fit a logistic model. Give an example. This example also demonstrates my SAS macro. Here I will demonstrate the weight of evidence coding for predictor D. We have a frequency table of D versus the binary response Y, and next to that we have the column percent for Y equals 0. Those percents add up to 100. We will refer to those percents as B sub J. Next to that, we have the column percent for Y equal 1, and we'll refer to them as G sub J. And then finally, on the right side, we have the weight of evidence calculation. It is the log of the ratio of those two column percents. Shown as a formula, we just pull off the weight of evidence from the right-hand column. Weight of evidence is widely used in credit risk modeling as an alternative to dummy variables. See the book by Siddiqui, Intelligent Credit Scoring. We can create dummy variables for D in a simple data step. Here it is. But more easily, we can use the class statement in Proc Logistic to create those same dummy variables. Here is the alternative approach using weight of evidence coding. Now I'll make some side comments regarding the binning of discrete predictor D. The modeler can enter D into a logistic model using weight of evidence coding or dummy variable coding. But either way, the modeler should consider binning of D. Binning reduces the number of levels of D while maintaining predictive power, and it simplifies the model, removes outliers, and improves validation on a holdout sample. To illustrate, here we have D with 4 levels, and we're going to bin together those bottom 2 levels. In my SAS Global Forum paper of 2017, I talk about SAS macros for binning predictors with a binary target. Why use weight of evidence coding? Weight of evidence has some desirable properties. Let's take discrete predictor D and other predictors that we'll call Z. And for discrete predictor D, we have the following relationship for its weight of evidence coding. The model log odds are linear versus the empirical log odds. Here is the equation that expresses that. On the left, we have the model log odds. And that, of course, is equal to the model's X beta. Inside X beta, we have the term involving the weight of evidence coding of D, and then other terms that we are holding fixed. And now recall that the weight of evidence coding of D gives us the empirical log odds. This relationship is not true for dummy variable coding of D. From the above, if D has an ordering and if the weight of evidence coding for D is monotonic versus D, then so is the model's probability. That probability is also monotonic versus D. This is not always true for dummy variables. Here are some other desirable properties of weight of evidence coding. Weight of evidence adds fewer parameters to a logistic model versus the use of dummy variable coding. Weight of evidence is numeric, and these variables can be compared to other numeric predictors to assess collinearity. And there is a natural connection between weight of evidence coding and the generation of risk model scorecards. See the book by Siddiqui on that topic. Let's consider models A and B. Both models involve discrete predictor D. In the case of model A, D appears in the class statement. In model B, it is weight of evidence coded. These two models produce exactly the same probabilities. In model A, D has L-1 degrees of freedom. Therefore, in model B, the weight of evidence coding for D must also have L-1 degrees of freedom. Let's now add a predictor to models A and B. We'll add predictor Z, a numeric predictor. Now these models, A and B, are not the same. They do not create the same probabilities. If we consider D as a collection of dummies, and we add it to the model Y equal Z, it will add L-1 degrees of freedom. Now, what about adding the weight of evidence coding of D to that same model, Y equals Z? How many degrees of freedom to assign to the weight of evidence coding of D? 1. But the weight of evidence coding of D had more than 1 degree of freedom in the earlier model. L-1, but is L-1 too much? The answer is that the degrees of freedom we should assign lies between 1 and L-1. But where? Why does it matter how many degrees of freedom to assign to the weight of evidence coding of D? Consider forward selection when fitting a logistic model, and suppose Z is already in the model. Now suppose the choice of the next predictor to enter is numeric X, or weight of evidence coded D. How to choose between those two? The degrees of freedom that we assign to the weight of evidence coding of D definitely matters, because it determines the p-value of the chi-square to enter. The chi-square probability depends on degrees of freedom. Or if we're using minimum AIC to pick the variable to enter, well, AIC depends on degrees of freedom. The normal practice when we are running PROC logistic or HP logistic is to assign 1 degree of freedom to the weight of evidence coding of D. There's really no alternative, no practical alternative. But this normal practice is unfair to X because the weight of evidence coding of D benefited heavily from the involvement of Y in its coding. Now, a quick reminder regarding the model comparison test. The model comparison test requires truly nested models. The restricted model is nested in the full model, where the full model uses every parameter in the restricted model plus some additional parameters. The test statistic, T, is the difference of the -2 log likelihoods from the two models. Here it is. For large samples, the distribution of T is chi-square with degrees of freedom equal to the formula that is shown. The degrees of freedom for the full model minus the degrees of freedom for the restricted model. Let t, small t, be the value of t from a sample. Specify your favorite alpha. If the right tail probability for the model comparison statistic exceeds alpha, then the restricted and full models are deemed statistically equal. Now I'll discuss a new kind of nesting. Consider discrete predictor D, numeric Z, and binary target Y. And we can then find the maximum likelihood estimates for the logistic model shown below. I'm calling that the WOL model. It involves the weighted evidence coding of D and the numeric predictor Z. I claim coefficients can always be found for the class model shown below, so that the WOL model and the class model have the same probabilities. These coefficients are derived by using the maximum likelihood estimates from the WOL model as a starting point. But these coefficients are not the maximum likelihood estimates for the class model. All this generalizes to multiple weighted evidence predictors and multiple predictor Z. This is the new nesting. The math behind this slide is given in the paper. Consider again the class model and the WOL model. Again, D is discrete, Z is numeric. As we discussed on the prior slide, we can regard these models as nested. Now, with some abuse, I can write down the model comparison statistic as the difference of the -2 log likelihoods for the WOL and class models. We have some unknowns. We do not know how to assign degrees of freedom to the model comparison statistic. We do know the degrees of freedom for the class model, and of course we do not know degrees of freedom for the WOL model. The degrees of freedom for the model comparison statistic must somehow be assigned. If we could do that, then we could determine the degrees of freedom for the WOL model. Here is the current state of affairs. We have the model comparison statistic, but we do not know the degrees of freedom to assign to that model comparison statistic. But we're going to figure that out on this slide. From the sample, we will compute the value of the model comparison statistic. We'll call that lowercase t. And now, given an alpha, there is k degrees of freedom so that the right tail probability for the model comparison statistic is equal to alpha for that given k degrees of freedom. K may be fractional. And this then gives us the definition of how to assign degrees of freedom to the model comparison statistic. It is that k. So for this k, the class and WOL models are just barely statistically equal. With this definition, we can write down the equation for degrees of freedom for the WOL model. The 1 degree of freedom for Z in the WOL model and class model cancels out, making the degrees of freedom for entry of the weighted evidence coding of D to the model Y equals Z to be given by the formula shown in the box. For example, suppose D has 5 levels, and suppose we determine that the model comparison statistic should be given 2.4 degrees of freedom. Then just plugging in the degrees of freedom for the weighted evidence coding of D on entry to the model would work out to be 1.6. This idea generalizes for any Z multiple predictors. Now we're ready to talk about the macro that I mentioned early on. This macro does forward selection, selecting predictors that give minimum AIC, but where we adjust the degrees of freedom in the case of weighted evidence coded predictors. The adjustment uses a formula that we have been discussing and was given on the prior slide. Underlying the macro is proc logistic or HP logistic. That's actually a user choice. And there's also an option to use BIC instead of AIC. Here is a data set called test, and we're going to be using that in our example. And notice that in the formula for the target Y, the classification variables C1 through C5 play no role. However, B1, B2, N1, and 2 do appear in the equation for the target variable Y. Here are the number of levels for the 5 classification variables. We're going to recode those as weight of evidence. Here is some of the code. We'll set alpha to be 0.05, and we're going to run the macro to fit a logistic model, and the predictors are listed below. There'll be 9 altogether. So we run the macro. The first 4 predictors to enter are no surprise, B2, N2, B1, N1. They're all involved in the equation for the target variable. Then the weighted evidence coding for C4 is entered. This is essentially by chance. It has adjusted degrees of freedom of 3.8. Minimum AIC is reached at step 5. And notice that none of the weighted evidence coded predictors had their degrees of freedom adjusted to 1. We now fool the macro so that C1 underscore WOE up through C5 underscore WOE are not regarded as weighted evidence coded predictors. The macro regards them as having just 1 degree of freedom. We run the macro and we get the first 4 variables just as expected. The minimum AIC is reached at step 8. 4 woes are entered, and remember, they're all unrelated to the target. So in this example, giving 1 degree freedom to the 5 woes damages the model by adding meaningless predictors and loss of parsimony. Let's now discuss the role of alpha. The modeler should regard alpha as a tuning parameter and not so much as type 1 error probability for hypothesis testing. The modeler may want to experiment with values of alpha before final model fitting has begun. For fixed sample size, if alpha is decreased to near 0, then the adjusted degrees of freedom for a weighted evidence coded predictor will reach L-1. Otherwise, if alpha is increased to near 1, then the adjusted degrees of freedom for a weighted evidence coded predictor will reach 1. The chi-square test is sensitive to sample size, and for large samples, the value of alpha should be decreased. Final comments. The adjustment of degrees of freedom is likely to reduce the entry of weighted evidence coded predictors into the model. This is simply because AIC involves degrees of freedom, of course smaller is better, and the WO adjustment increases degrees of freedom. Binning increases the chances for a weighted evidence coded predictor to enter the model. The reason is predictive power is largely maintained by binning, while binning reduces degrees of freedom. My macro runs pretty well, but it is computationally intensive. If there are n numeric predictors, and C, weighted evidence predictors, then the worst case number of calls to Proc Logistic or HV Logistic is given by the formula shown on the page. Notice that we have quadratic growth in the number of procedure calls versus the number of predictors. But the macro does have options to avoid long run times. We can set it to stop running when minimum AIC is reached, and we can also set it so that predictors that are known to be good are included. They're not part of the forward process. An example with 20 predictors and sample size 5,000 ran in about 15 seconds. But 200 predictors and sample size 100,000 is not practical. An upper limit, maybe 60 predictors and sample size 10,000. Thank you for your interest in this topic. Here is my contact information.